Okay. When the ions come in, okay, I actually want to flip to a little animation. There's an animation which actually shows this beautifully. Okay.
Did you do these too?
No, these were done professionally by an outside company. Oh yeah, I love these ones, are beautiful. Okay. Now, when the ion enters, now we get Lorentzian motion, which is an ion in a charged field undergoes your right-hand rule. So the magnetic field is going into the magnet, so the ions are revolving around that field in a clockwise motion. So the ions come in, hopefully pretty much in the center. Okay? And they're doing what's called the cyclotron motion. They're moving around the center of the axis in a mass to charge dependent frequency. So each ion in the trap is moving at a different frequency around the center. Okay? They are creating a current on my detect plates. Okay, except the problem is, as the charge moves near, it pushes electrons on one. As it moves near the other one, it pushes electrons, and we get a current. The problem is the ions are so close to the center that the difference in current between the two plates is almost zero. It's undetectable. It's too small. So what we've got to do is we've got to increase that current. And we increase that current by extending out their motion, by applying a pulse called an excite pulse. So we apply a pulse of RF to my excite plates. This causes the ion to gain kinetic energy. It's resonance excitation. Just like the dipolar caused the ion to do this, well, this caused the ion to spiral out.
So does it scan across all the amplitudes?
No, it does a stored waveform inverse Fourier transform. Just like the dipolar applies all the frequencies at once, we nail it with all the frequencies at once. Okay? And you see that the ion now moves closer to one plate, and then to the other, then to the first. And if we detect this, when it moves near a plate, it creates a current. And we actually see that as a sine wave on our oscilloscope, on the digitizer built into the computer. Does that make sense? Or is everyone completely 100% with me? We take this signal, we Fourier transform it, and we get out the frequency of motion. We then take our calibration equation, okay, which we did during our mass calibration. So now here's my second Fourier transform calibration, which is also divided into 6 parts. 3 positive, 3 negative across each mass range. Okay, so there's 6 excite calibrations. Now there's 6 mass calibrations. Okay, you guys with me? So my mass calibration allows me to fit this frequency to its mass.
Because you've controlled to some extent the number of lines in the trap.
Ah, we haven't got that yet. Hold on. Now, what happens when we put 2 different masses in? Okay, here's a very large mass and a very small mass. Notice
So they have the same radius, just different frequencies.
they have the same radius, different frequencies. Hence creating that overlapping look that I tried to draw for you earlier. Remember you were asking me, what does quadrupolar look with a dipolar on top? It looks almost exactly like that. Okay. We Fourier transform this transient, is what we call it, this time versus frequency, and we get out 2 lines, 2 different frequencies. Put the mass calibration, we get out the 2 masses. If we're eluting a bunch of peptides at once, we see something much more complicated, what we call the complex transient, which we Fourier transform, we epidize, we mode correct, we do a whole bunch of mathematics on, then we FT it, clean it up, signal to noise it, and display it as a spectrum for you.
Isn't the problem now automatic to have them all in the same radius where they're bumping into each other and interacting with each other?
Yes. Now, let's start talking about the complexities here. Okay. You'll notice that the big ions have the little ions pass them by. If you look at the big ions, you'll notice they kind of space themselves out because they're opposite charge, so they space themselves out. But you'll notice they get passed by the little ions. If you look at when I was just looking at one signal, notice there's never any ions passing him by. So when we have a complex mixture eluting, okay, one ion's frequency is changed by the ions moving next to him. And we call this space charge, the same exact concept we saw in the ion trap. We see the same thing on the Fourier transform. And what did space charge do to our mass measurement on the ion trap? But what, resolution was an observation. What did it do to the mass measurement?
Increase the error.
It increased the error. Did it increase the error randomly?
No, it went up.
It went up in mass. We observe the same phenomenon here. The more ions we put in, the more upshift, if they're different masses. I want this to be very clear. There's one very big difference between space charge in the ion trap and space charge in the FT. In the ion trap, all we care about is the number of ions. So we could have one species with 200,000 ions, or we could have 20 species that add up to 200,000 ions. We'll see the same space charge. On the FT, if I put 200,000 ions of a complex mixture, I get space charge. If I put 200,000 ions of one mass, I don't get space charge. Because the one mass ions are always moving at the same frequency. They don't do the crisscrossing. So they don't space charge.
So if there's 200,000, hypothetically 200,000 of the same mass, it's not going to happen, but some of them are going to be riding on top of each other.
They're close, but they don't space charge. It's only when they pass each other by. And you create that little RF type experience. So let's say you have a very complex mixture elute, but you want to have extremely high mass accuracy for one of those guys. You sim him. You do a data-dependent remeasurement of just him without all the other crap. You get very high mass accuracy. This is how Matthias Mann will do the first scan at 4 or 5 million ions. And then he'll remeasure one of those by itself at a good ion population, 200,000 ions, and he gets extremely high mass accuracy. He'll go from measurements of 5 or 6 ppm down to 0.1 or 0.2 ppm. Okay, does that make sense? Cool. Any questions about this process? Now, there is a downside to this kind of measurement. Is the ion hitting the detector? No, the ion is merely moving near the detector and imposing a current. It's called an image current detection method. It is not as sensitive as having the ion strike the detector like the ion trap does. Okay? So, the ion trap can detect a single ion with no problem. The FT will not get a usable signal for one ion. It requires at least 50 to 100 ion packet to get a measurable signal. So the number of ions we put into the trap has to be significantly higher. A typical setting for the ion trap might be 20 or 30,000 for full MS. A typical setting for the FT would be anywhere from 500,000 to 1,000,000 ions. Okay? It is less sensitive if time is a factor. So if you say, I'm going to give you the same amount of time to fill the trap, then the FT is less sensitive. If you say, time, I don't care how much time it takes to fill the trap, then their sensitivity is equivalent. Okay. Except the FT cheats. Okay. So I want to talk about that little cheat for a second. Remember I said there was some other mathematics? I said we're going to epidize, we're going to zero fill, okay, and then we're going to do an FT. Then we're going to do a bit more mathematics, and we're going to get a mass measurement. That bit more mathematics is a signal to noise reduction. The problem is, okay, to record this spectrum is 2 gigabytes of information. The FT records at such high resolution that to represent the peaks properly, it takes 2 gigabytes of data, okay, per spectrum. And you might acquire